Hi everyone, I'm here today to talk about frieze patterns. Here at the bottom of the slide is an example of a frieze pattern in architecture. In short, frieze patterns are two-dimensional patterns that respect certain reflections, symmetries, and translations and are repetitive in only one direction. Here is an example of a frieze pattern with numbers. The symmetries here may not be apparent, but we'll see later how each position is determined. The first frieze group is a step. The second and third frieze groups are hop and spinning hop. We'll notice here that both feet in the hop and the spinning hop are left feet and they don't contain any reflections. They are rotations and translations only. We also see the sidle and the spinning sidle. These encompass reflections as well as rotations and translations. Lastly, we have the jump and the spinning jump. These 7 groups allow us to clearly characterize the different compositions of reflections, rotations, and translations in frieze patterns. But let's go back to math and numbers. Here I have 5 different hexagons. We're going to talk about polygons with n sides, which are also known as n-gons. And we can connect the vertices of an n-gon in a way that creates triangles as shown here. You'll notice that I have numbers listed at each of the vertices of the final triangulated polygon. These numbers represent the number of triangles adjacent or next to each vertice. Here shows the possible triangulations of a hexagon. You can rotate these hexagons, but these are the 3 distinct ways to triangulate a hexagon. Here is an example of a multiplicative frieze pattern. This particular type follows the following pattern. For each diamond A, B, C, D, the relation AD minus BC equals 1 must be true. We can see here that the example 2, 2, 3, 1 follows this pattern because 2 times 2 is 4 and 3 times 1 is 3. 4 minus 3 equals 1. And this will be true for every diamond that you can find in this frieze pattern. A quick definition before moving on. We define the order of a frieze to be n if it has n minus 1 rows. So this particular frieze pattern has 5 rows, which would make it a frieze pattern of order 6. Now, connecting frieze patterns with n-gon. Here I have one of the hexagons that I looked at earlier. And we can create a frieze pattern from this hexagon. The first and last row of multiplicative friezes will always be 1. And then we can create the second row using these triangulated polygons by starting at one of the vertices and working clockwise around the hexagon infinitely long, because like I said earlier, frieze patterns repeat infinitely in one direction. So here for order 2, I've started at the top and I've gone down 4, 1, 2, 2, 2, back to 1. And you can see that's what shows up in this second row. We can then finish down the frieze pattern with the rest of the rows by using the formula shown on the previous slide. These patterns are typically called Conway-Coxeter frieze patterns. And that is after their founding fathers, John Conway and Harold Scott MacDonald Coxeter. Here is a generic representation of a frieze of order n using an n-gon with values a sub I corresponding to the triangles adjacent to each vertice as shown in the triangulated polygons before. Now about some results. If we consider a frieze of order 4, I claim that it is not possible for A0 to equal A1. Here I've produced a frieze of order 4 using the triangulated polygon. And according to the diamond patterns, as shown previously, the following relationship needs to be true. A0 times A1 minus 1 times 1 must equal 1, which shows us that A0 times A1 must equal 2. Since 2 is a prime number, the factors of 2 are 1 and 2 only. So either A sub 0 must equal 1 and A1 must equal 2, or vice versa. Our second interesting result is in a triangulated polygon with n greater than 3, as shown below. At least 2 of the A sub i's are 1, and no 2 consecutive A sub i's are 1. This is really interesting, and the proof is pretty long, so I encourage you to check it out on the paper, but we do not have time for it here today. Now to additive friezes. Multiplicative friezes are not the only type of frieze pattern. Additive friezes have zeros in their first and last row. You might have noticed that this is the additive identity, similar to the multiplicative friezes with ones in the first and last row. Their relation changes slightly by replacing the multiplication with addition. So for every A, B, C, D diamond, as shown before, we now have the relation quantity AD minus quantity BC must equal 1. Let's talk about another type of addition, NIM addition. To do this type of addition, we need to look at the binary representation of each number. Consider 3 NIM plus or NIM sum 6, where this O plus is the symbol for the NIM addition. 3 in binary is 0, 1, 1, and 6 in binary is 1, 1, 0. Consider how we would add them using the rules of binary addition without carrying over. By that I mean 0 plus 1 equals 1, 1 plus 0 equals 1, 0 plus 0 equals 0, as in binary. But normally in binary, 1 plus 1 would equal 1, 0. Whereas in NIM sum, it is actually 0, because the 1 that we would normally carry over magically disappears. Here, our result shows us that 3 NIM sum 6 equals 1, 0, 1, which is the binary representation for 5, meaning 3 NIM sum 6 must equal 5. Using the same process, we can see that 6 NIM sum 2 equals 4. Now, what does NIM addition have to do with friezes? Well, there's another type of additive frieze pattern that uses NIM addition. In a NIM frieze, we have the similar pattern for the ABCD diamond, where A NIM sum D minus quantity B NIM sum C must equal 1. You'll notice the NIM sum from the previous slides show up in the diamond right here. 3 NIM sum 6 and 6 NIM sum 2. We saw that 3 NIM sum 6 was 5 and 6 NIM sum 2 was 4. Since 5 minus 4 is equal to 1, we know that this holds true for our NIM sum pattern. Here are my references, and thank you so much for watching.